হ্যালো এভরিওয়ান। আই থিঙ্ক আমাকে সবাই মনে রেখেছে এখনো। হ্যাঁ, অবভিয়াসলি একটা ইন্ট্রো তো অলরেডি আমরা আপলোড করিয়েছি। তো যেভাবে বলেছিলাম আজ মানে 21 তারিখ এবং 22 তারিখ 10টা লেকচার সিরিজ আসবে, সেভাবেই এখন আমি ইন্ট্রোডিউস করতে যাচ্ছি প্রিয়ঙ্কর দে সরকার, মানে আমার অনলি প্রিয়ঙ্কর দে সরকার। হি উইল বি letting you understand about a topic which is called cosmic conspiracy, and আশা করছি খুব ভালো বোঝাবে। মিডিয়ামটা ইংলিশে রাখা হচ্ছে as if it will be very much interesting in, it's like মানে এইভাবে বোঝালেই আই গেস ও এটা স্বচ্ছন্দ বোধ করছিল, তাই ইংলিশটা রাখা হয়েছে। আশা করি কেউ এটা নিয়ে কোনো কিছু মনে করবে না। আমরা ইংলিশ বেঙ্গলি তো জানোই, দুইটাই একসাথে করি। তো ওভার টু ইউ প্রিয়ঙ্কর।
Welcome everyone. We are here in a series of lectures that is conducted under the organization Juvenile Gurukul, a step towards a quality education at minimum expenses. I am Priyankar Desharkar and my lecture topic today is Cosmic Conspiracy, Cosmic Rays and Ozone Hole. And I am conducting this lecture under Juvenile Gurukul today on the completion of the third year of their tireless work in uplifting education among young minds. So, I'm here to give some light on the topic, this cosmic conspiracy, and to give not quite informative but a brief research research intuition to the students. Let's start from this point. We have the topic as cosmic rays and ozone hole. So we need to know what ozone hole is. And before that, we need to know what is ozone. So what is ozone? Ozone is very simple. It's a molecule of three oxygen atoms that has three that is bounded by covalent bonds. Two covalent bonds. One, the central oxygen atom is partial positive charge, while the others are partial negative charges. The bond angle is 116.8 degrees with the bond length being 1.278 angstroms. However, all these properties are not quite relevant here. These are the properties of the chemists. So not quite meddling with these topics, we will directly go to the concept of ozone hole. Now what is ozone hole? Ozone hole is not something we say a hole in a body. Here ozone forms a thin layer in the stratosphere, a very thin layer, that is with thin we don't mean thinness of the order of a paper. Thinness means with respect to the layers of the other atmosphere, means with the other layers of the atmosphere, the ozone layer is comparatively thin. Now what happened is, due to some reasons, the ozone concentration continued to decrease in the in the ozone layer. Due to the decrease of ozone concentration, there was thinning of the ozone layer, which made this layer thinner and thinner, and we call this a hole in the ozone layer. And this itself is called ozone depletion, ozone hole depletion, because the ozone hole is continuously getting depleted as well. This is a basic trend from the year 1971 to 2020 and further to 2065. Here what we can see is in the 1971 it is a very thin depletion, or we can say in other words the depletion is very small. As the time proceeds, see, there is a decrease in the ozone concentration. There is a decrease in the ozone concentration, and gradually the ozone layer becomes thinner and thinner, and the ozone hole becomes more and more depleted. The more now after this certain time, this 2020, 2017 is most, when we go to 2020 and cross further, we find that ozone concentration continues to increase now, and there is a increase in this concentration. So this bluishness in the ozone hole, that is, the bluishness here represents the very low concentration of ozone, that starts diminishing. That is, the ozone concentration is now increasing. See, it is a 2017 to 2041, there is a less bluish nature, that is increase in the ozone concentration. As we go from 2041 to 2065, the ozone concentration has increased much, however not as 1971. These white dots and these red dots, these are the ozone depletions caused due to two specific factors, right? So the white ones are the white dots that are actually created due to the topic we're discussing, that is cosmic rays, and the red dots over this region are due to the photolysis effect or the photochemical climate effect. We'll understand this later, and so let's go in the latter part. Yep. So we have this topic. Why ozone hole atoll arises? The first concept is the photochemistry climate model. This is an illustrative image of ozone depletion. So this is the sun, and the sun is emitting three kinds of UV radiations: UVC, UVB, and UVA. Look at the extent of UVA entering the Earth's atmosphere. UVA is entering very close to the Earth's surface, almost reaching the Earth's surface. Hence, it is crossing the troposphere and actually the ozone layer. The UVB can cross the ozone layer and reach the troposphere, but cannot cross the troposphere, whereas UVC gets trapped within the stratosphere. These UVA and B, they contribute the most in ozone depletion. Now, how do they contribute the most? That is rather seen from here. We see this equation CF2Cl2 when it acts with H nu. What is this H nu? H nu is the UV radiation. H nu gives CF2Cl free radical plus Cl free radical, chlorine free radical. This chlorine free radical reacts with ozone O3 and gives ClO and O2. The ClO further reacts with the oxygen free radical and gives chlorine free radical plus O2. Now this chlorine free radical can again go and react with O3 and give ClO and O2, and this process will continue. This process will continue. And what kind of this process will continue? It will give a avalanche of production of Cl free radicals. Large number of Cl free radicals will be produced. Large amount of O3 will be decomposed. Hence, the concentration of O3 will be reduced in the atmosphere. We'll have the ozone hole. The most simple model of ozone hole depletion. However, this model couldn't explain certain aspects. What this model couldn't explain? The very basic thing this model couldn't explain was a thought, as it suggests, a thought that we know that the earth revolves around the sun. So as the earth is revolving around the sun, as the sun rays or the solar radiation is reaching the earth, and as the earth revolves around the sun, we have the 4 seasons. So in summer, the solar radiation reaching the Antarctic region is the most, which is much lower in the winter season. Then what's the statement? That this suggests that in the winter season, ozone depletion should be very less. It shouldn't be at all. Ozone depletion shouldn't be at all. And ozone layer should regain its original form in this winter months. Again, it will deplete in the month of summer. And as it is continuously depleting in the month of summer, this ozone depletion will stay for a considerably longer period of time. Okay, but that's not the case. So this is suggested basically the photochemical climate model, but it is seen that ozone continues to deplete even in the month of winters. And so I'm asking question that is there any specific reason for this? Well, one specific reason one can say that something is coming from outer space. Something is coming from space and it's causing this problem with the ozone in the hole and in the ozone layer. At the first thought it may sound something very absurd because something is coming from space, it's causing some problems that are that's pretty different difficult, that is looking that is we think it of as a science fiction movie, aliens coming and all sorts of discussions, but that's not the case. Neither of these causes it. To be very scientific, to go with this concept of physics, or not, let's not go directly with physics, to be very scientific, this is particularly caused by some particles coming from space, outer space. These particles have high energies, and these particles constitute the cosmic rays. We are introducing this term cosmic rays. So CFCs that are not the only culprits for ozone depletion. There are some other factors involved. So we bring in the fact of cosmic rays, which is the other villain in the story, so-called villain. It is 10 times more dangerous than CFC. Believe it or not, it's 10 times more dangerous than CFC. Cosmic rays are the main villain. They're 10 times more dangerous than CFC. Mark that, emphasizing on 10 times more dangerous. Because gradually, when we'll proceed with this series, we'll see that it is very difficult to remove cosmic rays. A cosmic rays is inevitable. So what are cosmic rays? I have answered it earlier in a very brief sense, but now we will go for its rather broader sense. Let's go for a brief idea of cosmic rays. So cosmic rays, we have an illustration also here. This is an illustration. And let's say cosmic rays were discovered by Victor Hess in 1912 in his balloon experiments. Now, what were his balloon experiments? Let me give a very brief idea of these balloon experiments. Victor Hess, a scientist, he made high energetic particles. Even he made incident radiations of higher energies directly on some condensed forms of gases. Now these condensed forms were of gases like chlorofluorocarbons or some other halogen containing gases. And he found out the true nature of cosmic rays, the very basic particles, or the basic particular nature, and how these cosmic rays were causing some problems with this kind of atoms or with this kind of molecules. From there, he discovered cosmic rays. He won the Nobel Prize in 1912. And he won the Nobel Prize in 1912, maybe in some later stages, but his experiments were conducted in 1912. Now, coming to the fact of cosmic rays, the high energetic particles or photons that travel through space with speed nearly equal to the speed of light. These cosmic rays originate from the sun. They may come from outside our solar system as well in the form of galactic cosmic rays. See, we have mentioned here. These are the galactic cosmic rays coming from Milky Way galaxy that is outside the solar system. These are the solar energetic particles. All these, they are influenced by the Earth's magnetic field. So let's again come to the nature of cosmic rays. Well, we cannot come to the nature of cosmic rays. It's not discovered yet. To be frank, it's not discovered yet. But we can merely say that cosmic rays 99% nuclei of well-known atoms, 1% of solitary electrons, high energetic particles. About 90% are simple protons, 9% are alpha particles identical to helium nuclei, and 1% are nuclei of heavier elements called HZD ions. Now these fractions vary highly over energy range of cosmic rays. Even a small fraction may contain antimatter, such as positrons or antipositrons. However, still research is going on to find the exact nature of this cosmic rays. To find the exact nature of this cosmic rays. So that's a very important point in research, that the nature of cosmic rays are not yet discovered. Cosmic rays are one of the most important topics in the field of astrophysics, astroparticle physics, even for high energy physics. A detailed analysis of cosmic rays is still awaited, and anyone interested can read a lot about these cosmic rays. There are numerous papers on cosmic rays and can have a better insight to these cosmic rays and what they are or what's their true nature. And maybe anyone can obtain a paper on this exact nature. Exactly. Coming to the next part. Now, how cosmic rays bring about the problem. We have discussed a very beautiful topic of cosmic rays, but that's the villain we have seen. Now we have informed you all that that's the villain. Now why that's the villain? Let's come to the point. The main problem with cosmic rays is that they are high energetic particles. They're made up of high energetic particles. Being highly energetic, they have a high probability that they will interact with halogen containing molecules, generate halogen ions, and which may convert themselves into highly reactive halogen atoms, and that will cause ozone destruction. And this is what happens to the ozone hole. To explain this, scientist Q Bin Liu, he brought out this concept of cosmic ray driven electron induced mechanism, or the CRE mechanism. Now that's a very detailed mechanism. We cannot go into its details because for understanding it we need to have three important mathematical tools. One is the time series, one is the wavelet analysis, then the third one is the square coherence analysis, and fourth one is the OHS and GCR analysis. The OHS is the ozone hole series and the GCR is the global cosmic ray flux analysis. So those are quite beyond our scope. We cannot go into its very details. But what we can say is this. A very basic model. How we can go through it. Let's see. See. The cosmic rays, they're actually incident on these halogen containing molecules. These halogen containing molecules CFC, HCl, ClONO2, these are actually present in polar stratospheric clouds. Now what are these polar stratospheric clouds? Polar stratospheric clouds are a densely populated collection of these halogen containing molecules. They form a layer just above the south pole in the stratosphere region, and they are being densely populated. They are called clouds, and that is itself the polar stratospheric clouds. Now these polar stratospheric clouds are quite important because they are the places that hold these halogen containing molecules in the time of winters. When cosmic rays are incident on these polar stratospheric clouds, they tend to ionize these halogen atoms, giving halogen ions. These halogen ions in turn get converted into a series of events to give highly reactive halogen atoms. These highly reactive halogen atoms can easily decompose ozone. The reactions will be same as that of the photolysis. For chlorine to get decompose ozone, the reactions will be same as that of photolysis. However, there will be some difference that now it is not induced by UV radiation. However, it is induced by cosmic rays and on polar stratospheric light. That's not the case in case of photochemical. This particular mechanism is considered very important because this could explain actually this CRE mechanism. This could explain one phenomena that could not be explained by the photochemical effect. That is the ozone depletion in the lower stratospheric region. In the higher stratospheric region, that was explained well by photochemical effect. However, in the lower stratospheric region, there was some problem because in the lower stratospheric region, the CFC's concentration was not as high as that of the higher stratospheric region. So for that, this cosmic ray mechanism was developed. So now this is a very theoretical approach. It also has a quantitative approach. Let's see this quantitative approach. The mathematical form of the CRE mechanism, right? So that is mathematical form will particularly relate the change in the total ozone with the cosmic ray intensity. This is the relation. The percentage change in total ozone will be equal to minus k times within square bracket C into I square, where square bracket C is the equivalent effective chlorine concentration in the polar stratosphere and capital I is the cosmic ray intensity. This is well celebrated equation that depicts the CRE model, and this will prove to be very efficient when we'll explain the experimental observations, when we'll go to the experimental observations. It's just in the next slide I think we'll be going to the experimental observations. So let's directly go to the concept of the effective equivalent chlorine concentration and the cosmic ray intensity variations over the years. This is the graph. This is a time series of ECL and cosmic ray intensity. There is some sort of Fourier transform of this function in the domain of time. There is a time series and plotted against time. This gives the time series. The x-axis here contains the years from 1970 to 2020, and the y-axis is the ECL or the cosmic ray intensity. So what we find is this part that up to a year of around 2003-4, the ECL concentration was increasing and it reached a peak around 2005 or 6. From there it got reduced for both the midnight hues and the Antarctic region. Now, as this ECL got reduced, according to the photochemical model, there should be a decrease in the ozone depletion. There is ozone would start repairing because there will be a lesser concentration of the halogen atoms. The lesser concentration of the halogen atoms will mainly prevent the more decomposition of ozone and will get more ozone available and the depletion will be reduced. However, it is not the case because CR intensity continues to increase and that becomes a culprit there. Let's check it out. What we have here is the experimental observations for the total ozone. The experimental observations for the total ozone, that's at some point that is the main motto here. See, this is the first one, and this is the second one. What does these two signify? The reason that I have plotted them together is somewhat very significant. Let's look into it very closely. We have the total column ozone in the y-axis, and the x-axis is again the year. That means this is again a time series. Let's see this curve, the first one on the left. Between 1980 and 1990, there is a decrease in the total ozone as per the chemistry climate model. That is a photochemical model actually. And the observed ones also shows a decrease with certain peaks. Now those peaks couldn't be encountered, though that was done only with the CRE model. Right? The CRE model could fit well. So the CRE model could explain these observed peaks. Now what are these observed peaks? Both maxima and minima. These were actually ozone depletions. That is, total column ozone got reduced. It signified this. These points, these depletions, these minimas, these are the depletion in the ozone. And the same was for the annual near global. That is for the nearly the entire globe. The ozone concentration continued to reduce till 2005, and then according to CRE model, and then continue to increase. The observed 3-year smoothing was the same. However, the chemistry climate model could not fit well because it could only fit up to around 2003 or 4, and then it again got increased. This curve here will clearly suggest to us that the CRE model is very efficient in explaining this total ozone hole, means total column ozone concentration, and its change over the years. The graph on the right side is more significant based on this time. October to December, there is the winter months. We are making our calculations, but we are making our experiments with this cosmic rays with reference to this time, because it is this time when the solar radiation is minimum. So any explanation of decrease in the ozone, total ozone, will show truthfulness in the CRE model. So if we go again over these years, what we see from 1980 to 2020, we see there are peaks, maxima as well as minimas. The minimas are actually the ozone depletions. Maximas are relatively higher concentration of ozone. The 3-year smoothing curve is this black line, and the CRE curve almost fits over this 3-year smoothing curve, showing the CRE model is well efficient to explain the total ozone depletion or total column ozone concentrations over these years. These figures are actually taken as references from this the fingerprints of cosmically driven mechanism of the ozone hole by Quinn Bin Liu. So these two curves, the significance of these two curves cannot be neglected because they give the affirmation that the CRE model well satisfies the experimental observations. Now these readings were basically taken from a NASA observatory at Antarctica, South Pole, and all these readings, all these observations, all these graphs were actually made by them. So the next topic, the experimental observation of stratospheric temperature. Sounds a bit weird. The stratospheric temperatures. Ozone depletion has a very important, a very important effect, that is lowering of the stratospheric temperature. That is explained here. And over these years, there is the observed temperatures are lesser. There are minima here, CRE mean, and the CRE model, using the CRE model, we can easily explain this stratospheric temperature almost fixed. So the CRE model clearly explains the fact that the stratospheric temperature reduces due to ozone depletion. So CRE mechanism was seen to explain few characteristics of the ozone depletion. Now coming to a fact again that this is from October to December. This is again from October to December. If we go on in some respects here with respect to the properties of total ozone depletion or the stratospheric temperature decrease, and find that these all satisfy the CRE model, it is no doubt that the CRE model is well equipped with the idea that it fits with ozone depletion, or CRE model is well fitted with ozone depletion. This is the basic conclusion we can draw from here. The basic conclusion we can draw from that, because these experimental observations itself suggested that the CRE model was enough to explain ozone depletion along with the photochemical. That is basically what we conclude, that the CRE model could fit in with the time series variations of the total column ozone as is seen clearly from the corresponding graphs. Now this made a direct conclusive statement that the proposed CRE model was working well and quite physical in the system. Decrease in stratospheric temperature could also be explained with the CRE model, it being a direct conclusion of the ozone depletion. Hence the CRE mechanism could well explain the ozone depletion, and it came up as important phenomena for ozone hole depletion along with the photolysis effect, which is the photochemical effect. That's the basic conclusion of our discussion, that the CRE mechanism is going well with the concept of ozone depletion along with the photochemical effect. We cannot neglect the photochemical effect, as we have studied earlier. We cannot neglect photochemical effect because photochemical effect is working well for the higher stratospheric region. For the lower stratospheric region, photochemical effect fails, and we have the CRE mechanism. So if we want to satisfy for the entire stratospheric ozone region, we need to have both these models into consideration, the CRE model as well as the photochemical climate model. That's the way, the significance of the photochemical model as well as of the CRE model. And that's where we'll conclude this lecture. We have a few references. I'll go through them. Fingerprints of the cosmic ray driven mechanism of ozone hole by Quinn Liu. The influence of cosmic rays on the size of Antarctic ozone hole by M. Alvarez Madrigal and J. Perez Peraza and V. M. Velasco. And Fleming, Eric and Newman, Paul and Leanne Quinn and Daniel John. The impact of continuing CFC-11 emissions on stratospheric ozone. This is a journal of geophysical research. So what we can say, this topic, the cosmic rays is quite interesting, but it would be more efficient if a large number of ideas could be obtained. We can have a brief insight there. Much of cosmic rays is not yet discovered. Cosmic rays find its importance in the field of astrophysics, in the field of astroparticle physics, in the field of high energy physics. Even a branch of astrophysics is solar astronomy. Cosmic rays find its place there as well. For stellar evolutions also, there may be some aspects of cosmic rays not yet discovered, but we can go for it, we can study it. Cosmic rays are high energy particles, but it may contain antimatter. It may contain antimatter. We don't know. In the near future, we may also obtain such concepts that we conclude antimatter itself is having such properties that it can have this ozone depletion. It can be a possibility because nothing is impossible. If that is well logical and that is found to be well logical in the future, it is possible. But there is a great insight into the field of research for this topic, this cosmic rays and ozone depletion. So yeah, that's the point. We conclude here. Thank you, everyone. Thank you, everyone. I'd like to thank the entire Juvenile Gurukul team for giving me this opportunity to show some light on this topic. I'm honored to be a part of this grand venture and looking forward to working with everyone in such tasks again. Thank you all.